session before lunch on the last day. That was really thanks a lot. No, it's really great to be here. I love QEC. I love this conference, and it's an honor to be able to present here. I'm going to be talking today about work that I did while I was still at Microsoft, which I left very recently, and this is a talk about a flexible framework for quantum resource estimation with quite a long list of authors that you can see here. It was a very collaborative project. Okay, so quantum resource estimation, what is that? Well, the idea is very simple. We want to estimate the resources such as runtime and number of qubits to implement a specific algorithm on a specific quantum computer, a specific design of a quantum computer. And this has a long history. There are many, many papers that have looked at resource estimates for these particular kinds of problems, and this is just a sample. This is a very, very small sample, but there are really many, many papers that do this. So what is the point? Why do people care about these things? Well, I would argue that quantum computing is entirely about resources. The whole motivation for our field is that we would like to be able to solve problems with far fewer resources than we would with a classical computer, and to understand the resources required is therefore clearly very important. But more specifically, absolute estimates of resources required can help to validate an overall approach for a quantum computer. First of all, if you have some plan, some design of a quantum computer that you want to implement, whenever you start to estimate resources, you're forced to work through the details, and you're forced to work through how different parts of your plan connect together, and that helps you to validate your overall approach. In addition to providing numbers, which give you some idea of how hard it would be to build in practice. But I think what's probably even more useful than that is relative estimates rather than absolute estimates. And relative estimates are useful for the obvious reason that maybe you have some benchmark, some standard approach to build a quantum computer, and you know if you use that standard approach to solve some particular problem like factoring, you would require some set of resources, some number of qubits, some runtime. And then you have some new idea, maybe it's a new quantum error correcting code, maybe it's something else, but you want to know, does that actually help? Does my new idea actually result in a reduced resource count? And having a resource estimate is what allows you to really check that and to motivate that your research is in fact impactful for this question. And in this talk, I'm going to talk not just about resource estimation, but about a flexible and modular framework for resource estimation. And so this really collects together these ideas that were already in the literature and tries to pull them together into something which is more holistic. And the reason to do this, there are a number. The first is just ease. We can do the same things that we've already been doing, but we can do it easier and faster by using this framework and the tool that comes from that framework to quickly validate new ideas rather than having to start from scratch and go through all the gory details ourselves. Also, for consistency, like I said, comparison is really the most important thing with these tools, in my opinion. And if you whoa, it's getting better up here. And if you have a framework and a tool already there that's modular, and you have some new idea that you can slot into that, you can be sure that the rest of the comparison is going to be apples and apples. So that's very useful too. And another thing which is maybe not so obvious, but I would like to highlight today, is that having a framework and a tool like this can actually help to motivate research. To build a resource estimation tool is really building a model of a quantum computer, and you can, by studying the model itself, you can identify areas that could be really impactful for research, questions that maybe we haven't looked at as much that can allow us to really highly impact the field by reducing resources. Okay, so in the rest of my talk, I'm going to essentially talk about these three things: how we design this framework in the first place, how you construct estimates using the framework, which will be most of the talk, and then I'll talk a little bit about the implications which we observe after having this framework, and essentially ideas that I think people should focus on, and I would like to focus myself on in order to reduce resources in future for quantum computing. Okay, so to design a quantum computer, we need to think a little bit back to basics, what does a quantum computer involve? Well, there was a very nice set of criteria, famous set of criteria, put down 23 years ago by DiVincenzo, and it essentially tells us what we would need to build a quantum computer in the first place. It's not everything that you would need, but it's a set of requirements, and they still hold true today. But since then, we've learned a lot, and we've learned in particular that when looking for algorithms for speed up, we are really going to need quite large algorithms if we want to have some practical advantage in our quantum computers. So if we want to have algorithms that actually run faster than anything you could do on a classical computer in practice. And those algorithms that we have so far discovered all seem to be quite large. And because they're quite large, the error rates that you would need for a quantum computer to run them must be very low. And the hardware that we can build is a big gap. So no surprise in this audience, we need QEC. And that's really going to be one of my main assumptions here. And the first thing I would like to state is that it seems like we should probably be adding a few more criteria to DiVincenzo's original ones to incorporate the fact that we know we're going to need QEC. So at a simple level, this means low error rate operations. We're going to need to operate below the threshold of some quantum error correcting code, and also parallel and well-connected operations. I want to go into a little bit more detail on that, which is really just a review of things that are already known. So the first is what error rates can we get away with? Well, the highest circuit level threshold that I know of is the one by CNIL, which is around 3% for depolarizing noise. It's interesting to consider these modified noise models where we may be able to push beyond that. But certainly we want, for practical purposes, to be well below those threshold values. In terms of connectivity, there have been a number of studies which I find quite remarkable, to be honest, that you can actually implement in a 1D chain, you can implement fault tolerance, which is quite surprising. However, the requirements for that, the resource requirements are very high. So I would say it doesn't necessarily meet the practicality. These proposals don't necessarily meet the practicality requirements. And also, they seem very vulnerable to fabrication defects. If you remove a qubit in a 1D plane or some operations, then you have now disconnected systems. 2D seems like a very big step up from that, and many schemes that we know in quantum error correction, of course, can be implemented in 2D. If we want to go to other codes like LDPC codes, then it seems very probable, although there's some interesting new ideas that we've heard at this conference, that you probably cannot achieve that practically with just 2D, and you probably need some higher, longer range connectivity. But it's interesting to explore alternatives. The other thing which I think is often, we all know this, but I like to put it in slides because I think sometimes it's not that known in the experimental communities, is that you really need to do these operations in parallel, or at least with some amount of parallelism. You can't do one thing after the other, or else errors build up. So that's what we need just for QEC. And if you then kind of take a step back and think about the different aspects that would be required to build the full quantum computer, I think that this picture is very helpful. This is really a stack for a quantum computer that's inspired largely by the stack that is used to understand classical computers. And the idea is that at the top of the stack, you have very abstract concepts and ideas. At the bottom of the stack, you have much more concrete ones. But that this stack should actually be filled in with consistent examples in order to be able to build a full quantum computer. What do I mean by that? Well, for example, the physical qubits down towards the bottom here, each layer is going to have some objects in it, some set of objects and some operations that are allowed. And at the physical qubit layer, we have these qubits represented by dots, and we must have some operations between them. For example, C-naughts between nearest neighbors, preparations, et cetera, et cetera. And then in the layer above, we have a more abstract thing. We have the quantum error correcting code. And in that layer, our objects are, of course, these codes, and the operations we need to be able to perform are, for example, check measurements on those codes. And these layers have to be consistent if we want to measure this check measurement at this layer of abstraction, we must be able to implement that using more detailed operations that are actually available in the layer below. And so this is essentially how we are going to think of a model of a quantum computer in terms of these layers, and they must be consistent with one another so that each operation in one layer can be achieved using operations at the layer below. And of course, if you continue up this picture, you get more and more abstract, and we lose the details of the code and just retain the fact that we have logical qubits and what the operations between those logical qubits are. And this will be very important for estimating resources. So to do that, we really just instantiate each of these layers with particular examples. So there's a lot of stuff on this slide. I won't go into details on each thing, but the idea is that at the top level, we have an algorithm, and that algorithm will be written in some high-level language. And that is not the same language that is most easy to work with whenever you're actually working with logical operations in some code, like the surface code. And so each layer, we have some set of examples that we would like to study, and edges in this kind of graph tell you which examples are consistent with one another. They're not all consistent with one another. So in order to actually estimate resources using a set of examples like this, we take the approach where we find a point in the middle of this stack, which we find quite concrete to think about, which is the logical qubit layer. And that logical qubit layer looks like this. We have these patches for example, surface codes, although this also applies to flock A codes, and some T factories. And we have the operations that you can perform on those, which, among a few other things, is essentially multi-qubit Pauli measurements and the production of T states. And the idea will be that we will compile an algorithm down into those operations, and for a particular algorithm, for a particular size, we will know from that compilation what number of operations we need, what circuit we need to implement, and the quality requirements to implement it, and then we will build that from the hardware. And that's how we will get our resources. And I'm going to go quite quickly through this because I think a lot of these concepts are pretty familiar to people in the audience. So in terms of the algorithms we looked at, they're really supposed to be as representative as possible of a wide range of practically important algorithms. And I think it's an unfortunate indicator of our field that two of those wide-ranging, very different examples are both essentially quantum chemistry. There aren't that many. But they're quite different in nature, the first two problems. So the first problem is a very small problem. It's the smallest problem that we could come up with that looks like it would be of interest to the scientific community. The next problem is much more industrial in its application. And then the last problem is, of course, factoring. Okay, so to compile these algorithms down, we need some compilation technique. And we use a two-step compilation, which is quite similar to the classical world. The front-end compilation goes from this program description, which you can see a toy example on the left, to essentially a quantum circuit. And that's going to be our intermediate layer of compilation. And the quantum circuit, for example, consists of these multi-qubit rotation gates and Cliffords. The difference between these is that R here can be non-Clifford, whereas the C is Clifford, and measurements, etc. And that's kind of a fairly straightforward front-end compilation idea. You just walk through the algorithm and print out the circuit. And then the back-end compilation, first I'm going to describe here this baseline approach that was mentioned by Daniel in his talk. And the idea is essentially that you first synthesize your rotations. So these rotation gates that could be non-Clifford get synthesized into something else, which is built out of Cliffords and T's. And then after that, you replace each T by an injection, so a T state that we know we can produce in our architecture, and commute the Cliffords through. So whenever you have a Clifford commuting through this Pauli circuit, you just modify the Paulis, and you end up with a circuit, which is just a sequence of Pauli measurements and T-state productions. And we can compress that down. And as was mentioned in Daniel's very nice talk, was that this is kind of a pain because we actually have to do all of these measurements one after the other. And the reason is because they have, because of the commuting through of the Cliffords, they have very large support. And so it slows down potentially our algorithm. But we can do it, so that's fine. We propose an improvement of this. I wouldn't say it goes all the way, but the idea that we propose is that we actually add a synthesis block so that instead of first decomposing your rotation gates, you can actually do that off the main block. And so the idea here is that, yeah, you want to build up a rotation, you do that off the main block, and that allows you, that frees the main block so that you can apply another gate. So it speeds you up a bit, but it's still not all the way. Okay, so I told you there were 3 example algorithms, and this is kind of the numbers you get for those 3 algorithms. So if you want to implement this quantum dynamics example, then you need a few hundred logical qubits, and the number of logical time steps after you compile down to this surface code architecture is 10 to the 5. And importantly, the precision requirements are also estimated there. Okay, so building up, I'm going to go over this very quickly because everybody in the audience knows these things very well. But the idea is we now need to build the hardware, the logical qubits that would achieve those requirements that we calculated for the algorithms. And so you can build for example, the surface code bigger and bigger to make it more and more precise, the information it encodes. And we don't just look at surface codes, we also look at the Hastings hack code or the Floquet code. And the idea is that there's some top level numbers that are very important for these, like how many qubits each code patch would require, which basically is some constant times d squared, because these are 2D codes. How long the logical time step would be as a result, which is proportional to d, or d is the code distance, and then importantly, what the error suppression will be. And these, of course, are extracted from simulations. But that's the basic idea. We also need to produce t's. Again, this is very standard, so I'm going to go over this quite quickly. But the approach is that you have some distillation circuit that you use iteratively, like the one on the right. This is a very standard one, which was essentially the original 15-to-1 Bravy and Kitaev one, although this implementation of it is from Litinsky. And we use a few different versions of that circuit, and you run this in iteration until you get better and better magic states. And between each round of distillation, you need to increase your code distance because you now are getting a more and more accurate T state. And again, you have some, representative behavior of this thing. It's kind of like a phenomenological description of your quantum computer, is that we have this model for how many qubits would it take to for each distillation round, and you can build this into an analysis for the cost of a factory for producing a particular type of T state, and the time that would be required too. And you can, for a range of different qubit parameters, so what I mean by that, I mean we take a set of qubits, we imagine that you're allowed any local 2D Clifford or any local 2D nearest neighbor Clifford, sorry, and any local measurements, and we have some precision requirements that they fail with some probability, and we take a few different examples of what those precisions would be, so 10 to the minus 3, 10 to the minus 4, and 10 to the minus 6, and we take a few different run times for the operations. It says microseconds here. What that really means is about 100 microseconds. And these are kind of just names for these different examples that we take, but we have very specific lists of the actual operation times and error probabilities that we assume. But the idea is they're supposed to be representative of pretty optimistic 2 versions each of pretty optimistic future qubits for different hardware types, trapped ions, superconducting, and Majorana. And the big difference really between these different ones is that the hope would be that Majoranas would be much lower error rates, and the trapped ion qubits are going to be a lot slower, about 3 orders of magnitude slower. And if you want to build logical qubits out of those, you can work out the costs of that, and the same for the T-states. And this example that I've shown here meets the requirements that would be needed for, I think, one of the examples, I can't remember which. But you do this for all of the examples. Okay, so I mean, it's no big surprise that the results suck. We're in big trouble. This is the simplest example here, and for some of the cases, for some of these example hardware types, you would need 1 million qubits for the smallest example. The runtimes are already, pretty long compared to what people talk about running quantum computers for today, up to hours. But remember, this is just the simple scientific understanding, the very, very simplest case that we think might be of interest. The business cases are much, much worse. So with the slow qubits, I think this is kind of the most alarming thing for me when I was first looking at these plots, when we were producing them, is that really the slow qubits are, so trapped ions and neutral atoms are really very, very slow runtimes. So into the centuries in certain cases. And again, these problem instances are not necessarily, huge best ever. These are kind of small-ish problem instances. So I would like to add yet another requirement to this list of things that I think will be needed for practical quantum advantage in the long term, and that would be fast gates. So I promised that I would take a step back and think about what we might be able to do as a community to improve upon these horrifying numbers. And so I would like to quickly highlight how much time do I have at the minute? Do we know? 3 minutes? Okay, that's good. I made these slides this morning during the other talk, so 3 minutes is probably quite good. So the first thing is what happens if we improve hardware? And I think this picture already kind of tells us what we need to know about that. So the first thing is that faster operations basically will improve things linearly. So it will improve runtime linearly. If you can speed up your operations without changing your error rates, then yeah, you just move left on this picture, which is clearly a good thing. I think the other thing, which is maybe a little bit more complicated to think about, is what happens if you continue to improve your gate fidelity. And because the error rate, logical error rate, goes like p to the power of d, we have a logarithmic relationship between code distance and error rate. So reducing error rate doesn't actually help all that much. So reducing the error rate by a factor of 10 in these plots between these examples gives you a factor of a few, maybe up to 5. And increasing it another 10 gives you another factor of maybe like less than that. So it's really, it's not a massive improvement to reduce error rate as long as you're a good bit below threshold. So I think that's kind of somewhat interesting if there's a bit of a trade-off that you can do. Better distillation. Well, the first thing, so okay, this is please don't try and read this, but this is the data that went into that plot. And if you look at, from that data, the factory ratio here, and this may not be a surprise to those of you who have thought a lot about distillation, for the big examples, which are the two at the bottom here, the percentage of the qubits that are required for the overall algorithm is very low. So it's much lower than, it's around 10 or below in most cases. And so that tells us that having better distillation for those bigger examples isn't really going to help very much. It might shave off 10% of the overhead. It's not going to change the time. And it would improve the smaller example, though. The smaller example is limited by distillation. I didn't give the best distillation example here. So you could already be able to improve that by using better distillation circuits, but probably it would still be pretty significantly limited. Something that I think is kind of interesting is that in all of these cases, the number of factories it's not close to one, it's quite large. And the number of times you use each factory is quite large too. So what that really means is that we can kind of think of these factories as continuous. And so what you want to do if you're going to make a distillation factory or some method of producing tea states better is reduce space-time. Not reducing space or time is fine, but space-time is really the relevant metric to reduce. And that's what will change these overhead numbers. And the other thing is that we can ask why are these factories such a small part of the overall quantum computer? And I think it comes back to Daniel's talk, compilation is terrible. So our compilation is so bad that most of our quantum computer is after compiling running very, very slowly. And so there's no need for our magic states to be produced at a higher rate. That's essentially what's happening. And so that's one of the things that I would like to highlight. I think compilation is an important problem to tackle. And if you look at the analysis here, the standard approach, you can notice that this block of qubits, of logical qubits here, is a 1D block. And that is also the case in our improved version, where we add this like extra synthesis block. We still have a one-dimensional connectivity on our logical qubits that we're using for compilation. And you can go, and if we're assuming that we have 2D qubits to build these codes, we should assume that we can build 2D logical qubit connectivity. And so we really ought to use that and to get better compilation, and it is possible to do that. There's very little work in this front. There's some of my own. If you go beyond 2D connectivity, then you can apply the technique that Daniel was talking about for active volume. But I think there's a lot of interesting work to be done there. Another thing is better quantum error correcting codes. That's probably the most relevant in this community. And I think this is very, very interesting. There's a lot of exciting new ideas. And I think that probably the thing I would like to really drive home here is that if you come up with a new quantum error correcting code or a new way to use one, this affects many, many layers of the stack. And I think it's really important to try and get a handle on how the other layers change. So here, for example, when we had the surface code, we know how to implement that with local gates in the layer below, and we know the logical operations that produces, and we have compilation algorithms which target those. If you replace the quantum error correcting layer by LDPC codes, then you're going to need to change all of those things, and we'll need even richer compilation algorithms. Okay, so I'm probably over time, and everybody wants lunch. My conclusions are listed here, and just a reminder of the research that I believe these ideas motivate are on the right. Thank you very much.
Thanks, Michael. I'm going to field questions, and we'll start over here with Ben.
Hey, Michael. So what if you could move the qubits around and then do transversal gates between code blocks? You didn't have to use lattice surgery anymore. What would happen then?
Yeah, I think that's, there are a number of ways to improve things that are brought about by having higher connectivity or being able to move things. I think it's certainly the case that it's going to improve. It's going to improve things. Yes, the analysis here was with lattice surgery, which has a time overhead that can be avoided by transverse gates, as you said. Yeah, so I think that would be great to look at.
Hi, Michael. Great talk. You mentioned thinking about compilation is going to be very important. And the folks at Microsoft think a lot about Majorana fermions at the physical level. You might imagine that people who want to simulate fermions at the top layer of your stack would want to use logical fermions in a computational model like the fermionic quantum circuit model. Does your resource estimation tool allow you to estimate the resources for algorithms represented in that model, or is it just at the qubit model layer, logical qubit layer?
Yeah, it's a great question, and I know the paper you're referring to. So one thing I would like to highlight is I think you can, the framework that I'm presenting here is really very general. The framework is is the notion that you should have these separate, well-defined, consistent layers, and then you can plug in whatever examples you want. So what I can say is that the tool that currently exists that you can play with does not allow for that, but that there is no reason that you can't add new examples, which provided you add examples so that there's at least one consistent path from the top, the algorithm, to the bottom, the hardware, then you can run estimates with that. If you were to do that right now, you would need to fill in a few new layers. So yeah, maybe that's an answer to your question.
Okay, thanks.
Question over here, last question.
So building 100 quantum computers is probably no more harder than building one. Is there any room for parallelization?
Yeah, it's a good question, although I don't know if I fully believe what you said. But I think that, so here there's, yeah, but let's talk about it afterwards. I mean, I think that you're quite limited in parallelization. It does remind me of something which makes this whole picture even worse, which I didn't describe, which is that the estimates that I gave were for one shot of a quantum algorithm. Typically, we're going to need many, many samples in order to build up some distribution of the output. And so, if you had already 100 quantum computers, you would probably be wanting to use them for that anyway, even if you could parallelize.
All right, on that sobering note, let's thank Michael and all the speakers from this morning's session. And it is lunchtime, and